Hello and welcome to the web series, ZeroPM Pieces. In the ZeroPM Pieces, the researchers in the project will tell you about one piece of the ZeroPM puzzle that they're working on. So without further ado, here comes a ZeroPM piece.
All right. Thank you very much. So I'm Todd Gouin, a research consultant based in the UK and part of Work Package 6 within the ZeroPM project. And I'm going to walk through the development and application of a multimedia activity model for evaluating the fate of persistent and mobile substances in soil, which represents a tool that could potentially be used to help assess or derive an estimate of exposure in groundwater systems as a surrogate for drinking water for human health. So the model that I'm using is based on the concept of fugacity. Fugacity is a concept that was introduced in 1901 by Lewis. It refers to the escaping tendency of a chemical. It has units of pressure, which makes it quite nice because you can effectively visualize chemicals as they move from areas of high pressure to low pressure until the pressure between different systems is at effectively equal. So you have equal fugacity between different matrices. This makes fugacity a convenient method for defining thermodynamic equilibrium criterion in that the equilibrium is reached when those fugacities are effectively equal between those systems. This modeling approach was first described by Don Mackay in 1979 in a very important publication titled Finding Fugacity Feasible. And in fact, this approach has been widely used and adopted in various regulatory tools across the globe, including in the use of e-uses to derive estimates of concentrations for organic chemicals that are used in commerce. In the space of thinking about persistent and mobile organic chemicals, I'm going to assume most people are familiar with those criteria are, but I just sort of list them here. And one of the things for mobile chemicals that's important to reflect upon is that they have, or they're defined based on their organic carbon water partition coefficient, with chemicals that are typically more water soluble and have low absorption potential being defined as being mobile. This group of chemicals, I think, though, is important to reflect upon in that there are a lot of ionizable organic chemicals within this particular domain. Modeling these chemicals needs to be reflected upon a little bit differently than what we might do for neutral organics. And that's because neutral organics, their interaction with organic carbon, for instance, is largely influenced by nondescript van der Waals interactions between the chemical and the organic carbon, whereas for ionizable organic chemicals, particularly those that are in an ionized state, there will be an increased tendency for those chemicals to have an electronic interaction with the surfaces that they come into contact with, which can have a significant impact on how they behave in different environmental systems. And so just to visualize this to a little bit in a qualitative way or semi-quantitative way, you can sort of imagine that you have organic bases and acids. Organic bases, and when they are entirely charged in the environment, will have a positive charge associated with them. And what we see is if we look at the KD values, which is a descriptor of how chemicals sorb to different environmental solids, you will see that the KD value is much higher than it is for the neutral fraction of that same chemical, whereas for acids, the charged form has a lower KD value than the neutral fraction. And this is entirely due to the fact that in the environment, there is a dominance of negatively charged surfaces that exist. And so for acids, there is a repulsive interaction between the negatively charged chemical and negatively charged surfaces, which reduces the absorption behavior as compared to the neutral form of the chemical. Whereas for bases, because they are positively charged, the electronic interaction is enhanced as a result of what's happening, and which is why you get a higher KD value for this group of chemicals. So recognizing that there are differences between organic acids and bases depending on the pKa of the substance and how it behaves in different environmental systems, I think is important to reflect upon because it has an implication for understanding the fate and subsequent exposure of those chemicals in different systems. To address the challenge for this group of chemicals, and there is another factor that we need to reflect upon, is that when we have ionizable organics, that the volatility of those chemicals, or the vapor pressure, is effectively negligible. This makes it somewhat questionable or challenging to apply a fugacity-based approach, which is really utilizes that vapor pressure associated with the chemical as a way to model how chemicals move from one system to another. To address this applicability domain challenge when looking at using fugacity, Stefan Trapp, Antonio Franco, and Don Mackay in 2010 published a paper which uses an analogous approach to the fugacity, which is described as an activity-based multimedia model. And in this way, we can now model both neutral form and the ionized fraction of the chemical in a way that's consistent with the fugacity approach in a multimedia system to understand the fate of chemicals in a multimedia environment. Now, one thing also important to bear in mind is that in this publication, the model does utilize various algorithms to describe the organic carbon-water partition coefficient, which is based on KOW. However, these algorithms also include the potential to address electronic interactions, particularly for bases, using that second algorithm that's defined. Of course, alternatively, if you have the measured KD value for a chemical, you can override the use of these algorithms to estimate KOC and just use the KD value, which would give you a better representation of the chemical that you're interested in that specific model environment. Most of the calculations I'm going to show you today are based on the algorithms that are shown here, but again, these can be overridden if we had the KD values available for us to us. So to provide an illustrative schematic of what this model structure looks like, it's a multimedia, multi-layer soil modeling system. The multi-layer soil compartment is presumed to be important, particularly for thinking about these mobile chemicals, and that we want to think about their fate across a soil horizon. So we have, for instance, an unsaturated surface soil, a deeper unsaturated soil system, and then the saturated soil or groundwater zone, which we use as a surrogate for the bank filtrate concentration that we use to try to understand what the drinking water concentration might be for human health. The model also couples the sediment compartment to that saturated soil zone. So if you're emitting a chemical onto soil, it has the potential to leach through this soil system into groundwater and can also potentially migrate into surface water, or vice versa. If you emit a chemical into surface water, it can also migrate into that groundwater soil zone, utilizing this coupling, which is based on Darcy's law. So we have this ability then to try to simulate chemicals across soil systems, which we can then parameterize in a more complex way than the generic environmental systems that we have, such as in the EUSIS, which just assumes a 20 centimeter soil depth and no saturated soil zone within it. In the Mackay type multimedia modeling universe, we have 4 levels of models, level 1, 2, 3, and 4. Here I'm going to present results of this activity associated with level 1, 3, and 4. Level 1 assumes a system that's at equilibrium and steady state. There are no advective or reaction loss processes accounted for in the level 1 calculation, whereas the level 2 calculation doesn't address these additional loss processes that might occur. Since we're assuming we're looking at chemicals that are persistent, the property associated with reactivity isn't perceived to be of value at this particular point. So that's why I'm not showing anything from the level 2 calculations, because it's effectively the same as the level 1 when you don't have any reaction taking place. The level 3 assumes a system that's at non-equilibrium and steady state, a little bit more realistic of an environmental system, and is actually the approach that's adopted in EUSIS, whereas level 4 assumes a system that's at non-equilibrium and non-steady state with respect to emissions into the environment. And so then we can consider the influence of time and how that might impact the fate and exposure of chemicals, such as our persistent and mobile substances. So for the level 1 calculations, I'd like to use a chemical space approach to try to understand what the model is doing across a large number of different types of chemicals with varying physical-chemical properties. And so we can take these hypothetical chemical properties, for instance, and input them into the model, where we assume there's no advective or reaction loss processes occurring, and then we can try to map out the fate of a chemical in such a system. So the chemical space diagram is effectively what we're doing in this particular context is we have, for instance, log KOW shown here along the x-axis and the log of the air-water partition coefficient shown along the y-axis. And I can input these physical chemical properties, these partition coefficients, into the model on a 1 by 1 degree log unit scale, and then collect output from the model, such as the mass fraction distribution of chemical across this space, and create a contour plot, which then tells me what is then the sensitivity of the partition coefficients of the chemicals in terms of influencing their fate in this multimedia system. So in this particular example, you can see that chemicals that are hydrophobic with log KOW is greater than about 4 are largely partitioning into this particular compartment, whereas chemicals on the other side of this tend to be more water soluble, have a negligible partitioning into this particular zone when we reflect on the mass fraction distribution of the chemical across this space. Now, remember, this is a system that's at equilibrium and steady state. We can then do this for the specific model environmental system that I have parameterized for air, unsaturated soil, surface water, and for the saturated soil zone shown here. And what you can quickly see is that chemicals that tend to be volatile are effectively partitioning or have a mass distribution that's entirely in the atmosphere with negligible amounts in the soil compartment, whereas for chemicals that have higher hydrophobicity, they're effectively distributed between the unsaturated and saturated soil zones. The main difference between how I've treated the unsaturated soil and saturated soil zone in the parameterization in this particular example relates to the assumption of the volume fraction of water that's in this system. So in the unsaturated soil zone, for instance, I am assuming that there's 20% water in the soil, whereas in the saturated zone, I assume that there's twice as much, or 40%. Now, this is assumed to be potentially important because one of the questions that one could ask is the approach that's described in the technical guidance document for estimating a drinking water concentration for human health, which is based on the unsaturated soils pore water concentration, so that 20 centimeter soil pore water concentration, any uses is used as that drinking water concentration. Is it conservative enough for chemicals that might be mobile, as these chemicals may have a higher potential to leach into that saturated soil zone? If we just look at the mass distribution in this particular context, you can see that for more water-soluble chemicals, that the mass distribution is slightly higher than it is in the saturated zone than it is in the unsaturated soil zone. We can do the same thing for ionizable organics. Things get a little bit more messy when trying to interpret what all of these plots mean. In this particular case, we're looking at differences, for instance, for organic acids shown along the top and organic bases shown along the bottom, and with varying pKa values that might be consistent with what, in terms of varying behavior in the environment for chemicals. So chemicals, for instance, that are going to be largely in the neutral form, given their pKa, relative to assumption that the pH in the environment is 7, will behave just as we saw for neutral organics. And so there's no real difference between what I just showed and what is being shown here, particularly for the panels that are in the lower right-hand corner and the upper left-hand corner. However, for acids and bases that are ionized, those being in the upper right-hand corner and the lower left-hand panel, you can see that the fraction in the saturated zone does increase quite a bit more than what we saw for the neutral form of those chemicals. And so the sorption behavior and the ionized state of these chemicals becomes an important factor that we also would like to consider in the model, and these, at least at the equilibrium steady state assumption, you can see what the implications are in terms of the mass distribution of those chemicals. Now, if I go back to the point around the influence of the assumption of the soil, the volume fraction of water in the soil, you can see that there is an opportunity to try to evaluate the implication that is assumed in the technical guidance document using that pore water concentration in the soil. Are the model results that I'm obtaining here significantly different than what we would see using the assumptions in the technical guidance document? So if I take the ratio of the mass distribution of the chemical in the saturated zone and that in the unsaturated zone, and really focus in on these chemicals that are more water soluble, you can see that the difference in the mass distribution is about a factor of 2. However, at the same time, let's recall that the assumption in terms of the volume fraction is also a factor of 2 difference. So 20% in the saturated zone, or 20% in the unsaturated zone, and 40% in the unsaturated zone and saturated zone. Actually, when you put this on a concentration basis, implies that there is no difference for a system that's at equilibrium and steady state in terms of the water concentration. So as a consequence of this, we could argue that the assumption that's used in the technical guidance document is sufficiently conservative for chemicals that might even be mobile, as opposed to only applying to hydrophobic organics. So with this, that should give some confidence that the use of that number derived from the technical guidance document would be sufficient for persistent and mobile chemicals. Nevertheless, we can also reflect on the non-equilibrium scenario, which is what we see in the uses, and whether or not that would make a difference, and also the utility of the model that I've developed for application for estimating concentrations in groundwater as a standalone tool. A key component of this, however, is trying to parameterize the soil compartment so that it's representative of the European system. Thankfully, I don't have to reinvent the wheel when thinking about what would represent a generic soil system across Europe, because this was done in the development of the focus soil models that were developed particularly for pesticide use, for estimating the leaching of chemicals across different soil systems. And so there already has been defined a number of different soil compartments across Europe, which are meant to reflect different scenarios that chemicals might encounter in the environment and how they might leach into groundwater. So I can utilize these soil systems as a way to parameterize the model that I have. Now, within ZeroPM, we have our phase 1 chemicals, which are in 3 groups of chemicals, those being PFAS, triazines, and the triazoles. And so we've been sort of focusing on this group of chemicals to ground truth a lot of the assumptions that we have, particularly in work package 6, in terms of developing a risk-based prioritization approach for these chemicals. And in this context, of course, I'm interested in deriving estimates of exposure for this group of chemicals and comparing at least the model results against monitoring data that might exist. In terms of parameterizing the model, what I'm going to show is results based on parameterization against the Hamburg scenario described in the focus models. I've used this scenario as it represents the worst case leaching soil, as it exceeds the target of the 80th percentile of soils in terms of leaching, and also because the soil horizons that are described within this for this particular Hamburg scenario lend themselves well to a multi-layer soil system that I have in the model environment. So I can utilize this to get a refined parameterization of the soil compartment for that upper and deeper unsaturated soil zones. Phase 1 chemicals, an unfortunate component in this context is that we don't actually have strong emission data readily available as an input into the model. And of course, emissions represent the most sensitive input parameter for a multimedia FATE model for trying to derive estimates of exposure. In this particular case, I've taken a crude approach where I'm using an estimate that is based on the tonnage bands, and I'm using the upper tonnage band, whereby I emit this chemical entirely to soil, or 100% to soil, and then compare the results obtained from the model to those reported in the environmental monitoring data that's been summarized from the European Environment Agency and the Y6 database for groundwater. So I'm doing the best I can to try to compare like for like. However, there are still perhaps caveats to reflect upon, which I will get to as we move through the slides. So the preliminary results, when we look at model data versus the European Environment Agency data set, is that you can see that the steady state model concentrations, at least for atrazine and tebuconazole, for instance, tend to be on the lower end of the distribution of concentrations that have been reported in the monitoring data, whereas PFOA is a little bit more towards the higher end for the when reflecting the difference between the steady state model concentration and that of the monitoring data. Now, the reason for these differences is likely entirely based on assumptions in the model, but also in terms of what the actual monitoring data reflect. As again, this is not necessarily an apples to oranges comparison. There is a lot that's going on in the monitoring data which may not be reflected in the model. And so the fact that I'm even 1 to 2 orders of magnitude in the ballpark of the monitoring data actually provides some confidence, particularly given the crude assumption of the emission estimate that I'm using in the model, gives me some confidence that the model can perform well if I had a very good system, well-defined system to parameterize and to compare against that monitoring data that's specific for one system only. So these system-dependent factors become important. The monitoring data reflects snapshots in time and space, and of course, the time that the samples are collected relative to the emission of the chemical with respect to the hydrodynamic properties of the groundwater system that we're looking at, and chemical-specific properties all compete against each other to influence the monitored concentration that we have. The calculations I showed for the level 3, of course, assume that we have a system that's at steady state. And so the monitoring data and the model data are not necessarily, of course, in this context, showing the exact same result. And so seeing a difference is something that we actually would like to see. And in fact, if the results look too good, I would be more suspicious than if they are showing the 1 to 2 orders of magnitude of what we see there. Now, lastly, what I also can reflect upon is the influence of time. And so what is the influence of, for instance, changes in emissions into the environment? And we can do this using a level 4 model calculation, which accounts for a non-steady state scenario in that environmental system. So here I'm just going to show results for 2 chemicals, largely contrasted based on their differences in hydrophobicity. So this is for PFOA and for tebuconazole. And what I first want to do is reflect on the time to steady state. So if I have a steady state emission into the environment, how long does it take for the concentration in different environmental compartments to reach a steady state level? And what you can see is for PFOA, the time to steady state is much quicker than it is for tebuconazole, which can be entirely attributed to the hydrophobicity difference between these 2 chemicals. So although the log KW is similar for these 2 chemicals, PFOA is a strong acid, and so in the model environment, it's being treated in terms of its sorption behavior as being entirely in the ionized state and being a negatively charged chemical. Its interaction with organic carbon is going to be significantly less than for the neutral fraction. And so we do see this quick time to steady state, at least for that chemical, and much longer for the more hydrophobic organic. And then if we reflect on what might happen in terms of a pulse emission, so in this particular case, what I'm showing is we have an emission that's occurring over 10 years. We then shut the emissions off, and I'm trying to understand how long does the system take to recover from that emission into the system initially. So again, similar to what I just showed, the time to steady state for PFOA is relatively quick, but so is the time for recovery, whereas tebuconazole with a higher hydrophobicity is taking longer to recover than for PFOA. Now, I have to say this is, in this instance, is entirely influenced by the assumption of the groundwater residence time. So because PFOA is entirely associated with, or highly soluble, and its fate is defined by the fate of the hydrology of the system you're looking at, and if it's in the groundwater, and here I'm assuming a groundwater residence time of 20 years, half of the chemical is effectively recovered or lost over a 10-year period of time after the emissions shut off. Now, of course, if the groundwater residence time is on the order of 100 years, you will see that that slope would not be as steep, but it's then becomes entirely dependent on what that groundwater residence time is, because that is what's driving everything in this particular context. Of course, if I increase the groundwater residence time, for this to see a slower recovery rate for PFOA, the recovery rate for tebuconazole will become very, very slow indeed. So it begins to give at least an indication of the relative importance of of understanding or appreciating the difference in terms of phys-chem properties, but also the assumptions that go into the residence time for the groundwater that you have. So key observations in this is, of course, that emission data represent a fundamental input parameter if we want to get reliable exposure estimates out of the model system we're working with. When we reflect on the environment-specific variability, how important it is, the emission uncertainty, of course, is very high, but it can be shown that the combination of the physical-chemical properties and the hydrologic and assumptions related to the hydrological residence time represent additional factors that need to be considered, as they do influence the model estimates of exposure, both in terms of the steady state assumption, but also in terms of when you want to reflect on the time component. The importance of monitoring data, I think, can't be underestimated. If we have monitoring data, these provide, I think, a valuable resource in terms of trying to estimate what human health risks are. However, if we're looking at the monitoring data, it's really key that the monitoring data are reliable and relevant, representative of the systems that we're considering. And so a lot of work needs to go into really scrutinize that monitoring data to make sure that it is fit for purpose. So just to conclude, both the physical chemical properties and environmental variables influence exposure concentrations in groundwater. The preliminary results show promise, but there are caveats in terms of the output that's there. The model's steady state concentrations can be shown to be in good agreement with monitoring data, but care needs to be is warranted not to overinterpret the results, and that a certain level of humility is needed to appreciate that the good comparison may simply be serendipitous and not necessarily a true reality of what's happening in the environment. So in this context, I think it's important to remember all models are wrong, some are useful. We can also say the same for monitoring data. It's just a question of how we can best interpret what that information is, but we can use the information in a complementary way, hopefully, to better understand what the implications are with respect to exposure. It is entirely important to appreciate that it's difficult to confidently ground truth the model results unless we have a very specific system that we're looking at that is well defined and has reliable and representative data associated with it. And indeed, to really ground truth this model, it would be great to apply the model parameterized for a specific site where we have this information, as I think it would strengthen the confidence in the overall modeling approach. And I have high degree of confidence that the model should work very well if we have good input data that goes into it. So with that, I conclude, and very happy to field any questions that may be out there.
ZeroPM. Zero pollution of persistent and mobile substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under Grant Agreement number 101036756.